working on section 3.4, welcome, and 3.4 is about concavity and second derivative. We're going to focus on day 2 here. Other video prior to this had day 1 on it. So day 2, this one is going to focus on the second derivative, but not to focus on concavity, but mainly to find relative extrema points. And if you recall, we have done first derivative with a sign chart to determine relative extrema. This looks at it from a different perspective. How can I use the second derivative to find max and mins? So here's the basic idea. The second derivative test for the local max and min. Suppose that f is a function that's differentiable on an open interval containing c, and we know that f prime of c equals 0. So that would tell me, right, that it is a critical point. And that is where I expect to find max and mins. So I know that I've got some key locations here that are potential max and mins, but which are they? Are they a maximum or are they a minimum? Well, the second derivative test can give us information about it, and that can help me not do a first derivative sign chart. So the second derivative, I know information about it such that the second derivative is greater than 0. In other words, second derivative is positive. Then f will have a minimum at c. The original function will have a minimum at c. Why does that work? Well, we know if this is a positive second derivative, this means we are concave up. We are concave up, centering on c. So if it's concave up in the region that c occurs, well then just by picturing it, you can see how this is the bottom of the area, and that makes c a minimum. Makes sense, doesn't it? F second derivative of c less than 0, I'm over here reading this, if the second derivative at c is less than 0, which means that I have a negative second derivative, which means that I have concave down situation, then I know that c will be a maximum, and look at the picture on that. Concave down, like a frown, put c at the top of this situation, and thus c must be a maximum. So I can use first derivative test to find and locate c. I can use second derivative test, knowing the concavity, whether it's opening upward or downward, to determine whether it's a max or a min. If the second derivative equals 0, or it doesn't exist, which is possible, then the second derivative test fails for me, and I will have to go back to the first derivative and use a sign chart. So there's no getting around it for that situation. But if it's clearly positive second derivative or clearly negative second derivative, I know concavity, and that is helps me with the placement of c, knowing whether it's at the bottom or at the peak. But if it's equal to 0, then you got to go back to sign chart. Let's just do one example and call it probably close to good. Use the second derivative test to determine if the critical points are relative extrema. So we are going to find our critical points, which means we're going to take the first derivative, set it equal to 0, or look at where the first derivative does not exist. And so first off, let's just find our first derivative. F prime of x is equal to 3x squared plus 6x minus 9. I want to set that equal to 0. So 0 is equal to factor out of 3, and it's going to leave me an x squared plus a 2x minus a 3. Factor that, and we will be looking at 0 equal to 3, x plus 3, x minus 1. From there, I can determine that I have 2 critical points. Those 2 critical points are located at x being negative 3 and x equaling 1, where our factors each turn to 0. Now let's take those critical points, x equals negative 3 and x equal 1, and run them into the second derivative test. So second derivative, working off of that first derivative up here, my second derivative is going to look like 6x plus 6. In order to find concavity, no, I don't have to find concavity. All I need to do is test out my critical points. Test out the critical points. And for that, I'm going to go f double prime of, one of them was at -3, so f double prime of -3 gives me 6 times -3 plus a 6. That makes -18 plus 6, which gives us -12. The second derivative at c is negative, which makes it concave down. So therefore, it's concave down. And that's going to place c up here at the top. Aha! C, this critical point, or x equals -3, is a relative maximum. We knew it was a critical point because the first derivative was equal to 0 at -3. And we realize now that the curvature at x equals -3 is concave downward. That places it at a max. Let's go through and test out the other critical point at 1. F double prime of 1 is 6 times 1 plus 6, that's 12, which is positive, and that means that I have concave up, and that places this c value, when c is 1, at the bottom. X equals 1 is a relative min. They're quick, aren't they? It's nice you don't have to go through the sign chart like we did in the previous section of section 3.3, where we used first derivative with sign charts to determine relative min and max. Here we get to use first derivative backed up by information on the second derivative at that particular point. And we could go through another one. However, I think you could probably get the idea. So I'm going to go ahead and pass on to what I'm looking for is number 53, and maybe that's underneath here. There it is. In exercise 53, sketch the graph of a function f given the following characteristics. So these are always a little bit challenging, I think. F of 2 equals 0 as well as f of 4 equals 0. Just reading this first information. Those give me points, don't they? Actual hard points. When I put in 2, I get out 0. When I put in 4, I get out 0. If I had a graph, which we're just going to pretend we do, 1, 2, 3, 4. We have 2 points already located on our function, 2 and 4, 0. Next up, it tells me that f of 3 is defined. So by that, it means, you know, x equals 3 exists as a point, at some point. We just don't know quite the height of it, what y value it takes on. F prime being less than 0 when x is less than 3. This is giving me information about the first derivative. It's telling me the first derivative is negative, right? When x is 3. At 3, the first derivative doesn't exist, and then the first derivative is positive when x is greater than 3. From these 3 pieces of information, I would probably take it into a quick little sign chart, and I would say it is negative when we are less than 3, and it was positive when we were greater than 3, and it doesn't exist at 3. So we've got an increasing, we've got a decreasing function followed by an increasing function, but this is not a critical point, right? It isn't a max or a min. It is an undefined slope there, or the derivative doesn't exist, might be a better way to say it. F prime does not exist there. Sharp point, asymptotic, something like that, right? And then it also tells me that the second derivative F double prime, let's label this one F prime, F double prime, not at 3 though, is negative and negative. Right here I get less than 0, so negative, negative. Concave down around it. So what would this possibly look like? Well, at 3, this region of 3 was kind of an interesting one. I've got to come through 2, and I know that it's a decreasing function followed by an increasing function. I think what I'm going to do is come into 3 with a sharp point and leave it. I made mine look like a cusp. Excuse me. So that should be fine. Decreasing function, increasing function, so first derivative's positive, first derivative's negative. Concave down, which fits what we needed, and this one is concave down over here as well. And then we'd get the derivative didn't exist at 3. I'm just going to go ahead and show you what the homework is, and you can focus on that and finish that one up.